Hi everyone, this is the Y9AU paper walkthrough for the assessment that you've just done. So I'm going to go through the answers. I'm going to go through how I think about the answers for any of the ones that you have got wrong, and maybe do a bit of an explanation around it. So while you're watching this, make sure your green pen in your paper, and anything big that you've learned about it, you green pen in your books. Okay, so we've got a student here talking about energy saving light bulb. We've got a 30 watt light bulb. It uses 600 joules of electrical energy in a certain period of time. And in that time it produces 450 joules of light. The rest of the energy is wasted. Calculate the energy wasted. Well, if it uses 450 of joules, 600 goes in, there must be 150 joules of wasted energy, because what you get in, you must get out. So you must get out 600 joules. So 150 would take 450 up to 600 joules out. And that goes out as heat, but please make sure you say where to. Heat to the surroundings, because something has to have that energy store. Calculate the efficiency of the bulb. Well, we take the useful energy out, which is 450 in this case, divided by 600, and that gets us 0.75. You times that by 100, and you get 75% if you want to express it as a percentage. Calculate the period of time in seconds during which the 600 joules is provided to the 30 watt light bulb. Two ways of doing this. The easier way is just thinking about what 30 watts means. Well, 30 watts means it gives out 30 joules every single second. And so you've got to work out how many seconds until it gets to 600 joules. And if you think about it like that, it's actually quite an easy thing to work out. But I'm going to show you how to rearrange the equation method. If we write down our equation, power is the rate of energy transfer, so it's energy over time. And we substitute in, we have 30 equals 600 over T, which I don't know and want to find out. We now want to find T. I've got to leave T on its own, but I can't really leave it on the bottom, because that'd leave me with an equation that says a number equals 1 over T. And that doesn't make any sense. Now, you could do that and flip it over, but what we'll do is we'll take the T up to the top. So I'm going to times by T to cancel it out. So T times 300 equals 600. I'm now going to get rid of the 30. So T times 30 equals 600. I'm now going to get rid of the 30 by dividing by 30. And that leaves T equals 600 divided by 30, which equals our answer of 20 seconds. Okay, we're on to the data question here. We've got the filament bulb, and we've got its power, lifetime and cost, and we're comparing it with the LED's power, lifetime and cost. And it says that this company gets some research. And why is it important to confirm that information independently? Why is it important to find out if this company has done it from an independent source, another scientist that isn't related to the company, essentially? And that's because we would have bias, or the company would be biased. Just note the spelling, please. A homeowner is thinking about replacing his filament bulbs with LED bulbs. Suggest reasons why the homeowner is likely to choose LED bulbs, but we've got to use information in the table. Well, we've got a couple of reasons. We've got a lower power, and we've got a longer lifetime, and that would get us one of those marks. We've described what we've seen in the table. We haven't really used it yet, though. Now, using the information, if we look at the lifetime here, if you do 50,000 divided by 1250, or you ask yourself the question, well, that LED bulb lasts a long time. How many filament bulbs would I have to buy to get the equivalent amount of light time? Well, you do that equation, calculation, 50,000 divided by 1250, 1,250, and you would realise you'd have to have 40 bulbs. So we would have to have, we get 40 times as much light time, essentially. But we've only got 8 times the cost. So you could actually say that the bulb is more cost effective, the LED bulb, because of that idea that 40 times the time that it's alive for, but only 8 times the cost. Other thing you could have done was say, well, actually, I need 40 bulbs, so that would actually cost me 2 times 40. It would cost me £80 for the filament bulb, whereas the LED bulb obviously will only cost me 1. Final bit, state one factor other than efficiency that's important. I didn't like the question here, so I've allowed a couple of things like cost because it doesn't technically rule that out. But you could have gone for the colour of the bulb. Some bulbs have a slightly different colour. Okay. Okay, this is an experiment. It's really important in any question like this that you carefully interrogate each line of what's being said. Look at the diagram in detail and try and work out what they're trying to do. Because where people have made mistakes is because they haven't interpreted what's happening very well. This here is a hot metal plate kept at a constant temperature. And we then got a temperature probe there and insulating material here. So they switch it on, and they switch the temperature probe on, and it connects up to a data logger, which basically records the temperature, and then it can be displayed on a computer. So you can get instant live data, essentially. So we switch it on. And so what happens is the hot metal plate will obviously lose its heat to the colder surroundings, and the heat will go through the insulating block to the temperature probe, and it will warm up that insulated block. And that's what we've seen here. We turn on the temperature probe, it still starts at room temperature and slowly increases over here until we reach a plateau there. Same for material, material B doesn't reach that top temperature, material C. So you've got to understand the idea that heat is going through here and the insulation is trying to stop the heat getting to the block. So that'll come up in a minute. So the next question we had was, we might flip back here. Which material was the best insulator? Well, if you're the best insulator, let's just recreate those graphs there. You had the one that did that, you had the one that did that, and you had the one that did that. Well, the one that is the best insulator is the one that obviously will not allow heat through as quickly, and therefore its temperature will not rise as much. Now, please bear in mind that heat is energy, and temperature is the is how hot something is. So heat is the amount of work that something can do due to its temperature, but temperature is different to how hot something is. A clear example of the difference between this is if you put 1,000 joules of heat into a cup, its temperature will rise a certain amount. If you put 1,000 degrees, so the same energy, into a swimming pool, its temperature will not rise by the same amount. You won't get a 20-degree rise in a swimming pool for 1,000 joules. So they are different things. So we've got to be careful about what we're saying there. Weird line. Okay, so in this case, the best insulator was C because its temperature does not rise as much, or its line is not as steep. That was this line here, the green line there. Back to this question, what was the temperature of the hot plate? Well, this is interpreting it. Well, you can find that from this bit here. Material A reached a flat line at the top, which I think was 80 degrees. So if you kind of got that, I knew that you understood what the experiment was going on. If you said something like 20, then I knew that you didn't quite understand what was going on with the experiment. Okay, another student repeated the experiment but doubled the thickness for all 3 materials. Suggest how that would affect the results. Well, if it's thicker material, it would obviously take longer for it to go through. So what you would see is, let's do dashed lines. You would have, for this material but thicker, probably a lower end temperature after 10 minutes. So it hasn't quite got as high. And you wouldn't have the same steepness of the line. It would be the same for the others. So you've got to talk about A, the final temperature, and B, the steepness of the line. They're the 2 different things that you could find from that graph. Okay, advantages of a data logger. The obvious one is there's no human error, especially something called parallax error. And that can be a little bit of an extension. Go and find out what parallax error is and draw a diagram. So if you've got decent marks on your paper and you've got a little bit of time on your hands, you go and find out what parallax error is. That'll be very useful to you, especially with some exam questions that will come up later. The other thing though is resolution. This one here, I can tell the difference between 38 and 39 degrees, so only a change in temperature of 1 degree I can understand. I could probably work out there. Now this one here, if you look at it, I think that is either 39 or is it 38? It's halfway. So what we would say is we can know the difference plus or minus half a degree. And we're going to get into that later on, something called uncertainty. But the resolution here is 1 degree, but it leads to a guess of plus or minus half a degree either side. This one here though goes to 1/10 of a degree, so it goes to 0.1. So it has a better resolution. And resolution is the smallest thing you can measure. Okay, we had thermal conductivity. You had to pick polyurethane foam because that had the lowest thermal conductivity. Conductivity is about how easily a material allows energy through, and the clue kind of is in that units there. No matter watts per metre, and I know it wasn't wrote very well because of the formatting, watts per metre degrees Celsius. What that means is, if we remember, watts are how many joules per second. It's saying how many joules per second per metre of material you have to get through. So literally the thickness of the block for a 1 degree difference. It'll be 9 there, and heat would travel that way, because remember, heat travels from hot to cold. So for a 1 degree temperature difference from 10 to 9 degrees, the thermal conductivity would tell you how many joules per second there is for each metre of material you have. So polyurethane foam for 1 mark. The second mark would be for explaining that means there'd be a lower rate of energy transfer. The rate is important because that's what watts refers to. Watts is the rate of energy transfer. So how many per second? Okay, we were then on to our equations now. So the kinetic energy equation is half mv squared. Dump the numbers in. E equals half, or 0.5 on a calculator, times 0.058 times 5 squared. Make sure you do the 5 squared first on your calculator. Times it by 0.5, times it by 0.058, and you would end up with an answer of, I think, 0.725 joules. Position A is tennis ball at maximum height. So how much gravitational potential energy has it got? Well, we did this to death with the skater on the little FET app a while ago. And you know that if you put 100 joules into that skater gravitational potential energy, how much kinetic energy would he have at the bottom? He'd have 100 joules. All of the energy from that store, that bucket, would end up going from GPE to kinetic energy. And then back up to the top, assuming there's no air resistance, the maximum you could get is 100 joules of GPE again. It's the same idea. Well, it's the same idea as literally this part of it. If you start off with 100 joules of kinetic energy, what's the maximum gravitational potential energy you can get? 100 joules. There's a way to spot it as well. It says 1 mark there. So we're not doing any calculating yet, we want a number. So the answer's the same, 0.725. The equation links those 3 things. It's the gravitational potential energy equation. Energy is mass times gravitational field strength times height, and it was good to see the amount of people who got that. The difficulty was substituting in correctly. That was disappointing, the amount of people that in some classes who didn't substitute in. So admittedly, some of you went a bit gung-ho and took this answer here. But if you read the question carefully, it's about position B, where it gives you a new type of amount of energy. So it's actually 0.38 joules. The mass is the same, so 0.058, I think, times 9.8 times the height, which I'm trying to find out. What we now need to do is simplify. So we're going to take those numbers there and simplify them, leaving h on its own. Which, if we rewrite this, it would give us 0.38 equals 0.5684 times h. And then we need to rearrange it. So we need to leave h as it is on its own and get rid of 0.5684 times. So we do the opposite. We divide. 0.5684 cancels that out, and so h works out to be 0.67 meters.